Okay, in section 3.4, we're going to talk about the second derivative test and concavity. So, when we look at this, and there's just a couple ways that they talk about this, but this is a, let me change colors, it's a concave down curve, and this one is concave up, so that's what we're going to be looking at, like what's the curvature of the function, and it's concave up. If the first derivative is increasing, it's going to be concave down if the first derivative is decreasing. So, and like I said, we can look at those two different types of curves. We're going to use the second derivative test for this, and we're saying if the second derivative exists and you have the second derivative is greater than 0, it's going to be concave up. If the second derivative is less than 0, we're going to have concave down. Now there's some guidelines for testing that, and so just like we've done before in the past with other things with the first derivative, here we're going to locate x values at which the second derivative is equal to 0 or the second derivative is undefined. Now previously we found critical numbers by taking the first derivative equal to 0 or the first derivative being undefined. Well, now today we're going to be working on point of inflection or inflection point, and that's where the second derivative is equal to 0 or the second derivative is undefined. And we're going to say possible points of inflection because just like before we have possible critical numbers. And a point of inflection is just going to be where concavity changes. Okay, it can either go from positive to negative or negative to positive, either way. And then so some of the guidelines for finding that is that we're going to be right here, and it'll say locate x values at which the second derivative is equal to 0 or the second derivative is undefined. Use those values to determine your test intervals. So we're going to find test intervals. Pick some values to plug in and try, and then test the sign of it at each of the intervals. So then we can determine the concavity if it's concave up or concave down to then make our assessment. So we're going to basically use these ideas, and we're going to look at some graphs of that to work some examples. Well, let me see. And so one of the first things you'll do is I'll say find the points of inflection and discuss the concavity of the graph. So we'll start with our first function. It's a fourth degree polynomial. It's differentiable, and we'll start with we need our second derivative equal to 0. So the first derivative equal to 0 finds our possible critical numbers, and we've done some work with that before, but our second derivative equal to 0 gives our possible inflection points, and that's what we're going to look for here. So the first thing we'll do is get our first derivative, and then after that we'll take the derivative of that to get our second derivative. Okay, so then we need to set our second derivative equal to 0 and factor out here. So we'll take out what 12x, so that would leave us with an x minus 2. Set each one of those equal to 0. So here we're just going to get x is equal to 0 and add 2 to both sides, and 2 is. So we have possible inflection points, and we say possible inflection points. Okay. And so we can plug that back in to see if we wanted x, y values of those. We could plug into the original function. We can say what is the f when the x value is 0 right here. Plug that back into the original equation, which is x to the 4th minus 4x to the 3rd. And that's the original, so I can plug in 0. And right there we would just get 0. So this would be the ordered pair when x was 0, y is 0. Okay, and for the other one, if I evaluated f at 2, go to your original function, which is the x to the 4th minus 4x to the 3rd, and plug in 2 this time, and evaluate that. We would get negative 16, so that ordered pair would be when x is 2, y is negative 16. Now those are possible inflection points. We're going to come over here and finish doing some more work to see if they in fact are, and this is the process for that. It says we're going to start with our possible inflection points and put them in order, so we have 0 and 2. To create test intervals, so what we want to do is we want to pick any value to the left of 0. I'm just going to pick negative 1. You can choose anything. I could choose negative 3, negative 5. Negative 1's just easier because it's going to be easy to work with. Pick a value between 0 and 2. I'm just going to choose 1. And then I'm going to pick a value that's greater than 2. And I'm just going to choose 3. You have options in these test intervals with these green values that I'm choosing. It doesn't have to be the same number that I'm using, but it needs to be either to the left or the right of our possible inflection point and be valid. Okay, and we're going to call these our test values. And so you're going to take your test values and you want to plug them into your second derivative at that point. So my first one I'm going to test is going to be negative 1. Okay, so I'm going to plug in negative 1 there. So that means go to your second derivative right here, which is 12x squared minus 24x, and we're going to plug in negative 1. And when you do the calculation on that, we get 36. Well, all we care about is this number positive or negative? In this case, it's positive, so positive value. So I just come here, look at that, and then I move to my next test interval, which is going to be, I'm going to take the second derivative, and I'm going to test it at my second one, which is here. So I'm going to choose to test it when x is 1. So then I'll have 12 times 1 squared minus 24 times 1. And when you plug that in, you're going to get negative 12. All you care about is this number positive or negative? In this case, it's negative. So I'm going to put negative here. And then I'm going to move to test my last one. So now I'm going to be plugging in and testing my last interval. So I'm going to evaluate f double prom, substituting my test value of a 3 in. So plug in 3 everywhere that there's an x. I'm going to plug in a 3 here, evaluate that, and I get positive 36. So all we care about is it positive or negative? So we found out that it's positive. And then now what we look to see is, does it change from positive to negative or negative to positive? So since this went from right here, this goes from a positive value to a negative value, then we know that that's an inflection point. So for sure, there's an inflection point and concavity happens. Okay? And then also, if it goes from negative to positive, then there's also a change. That means that is an inflection point. Okay, so now we know that happened. So this is an inflection point, this is an inflection point, and now we're going to say this is concave up, this one's concave down, and this is concave up. So when you name that, your concavity is described in this manner. I would say concave up, let me not put it like that. It's concave up on the interval here, so negative infinity to 0, and then it's concave up from here on, so from 2, I'll say and 2 2 to infinity. It's concave down in the middle, so it's concave down from 0 to 2. So you name the interval as if it was on the number line. So I'm going to kind of sum that back up. The first thing you want to do is use the second derivative test to find possible inflection points. And we said possible because they're only inflection points if, when you test them over here on the right side, if it goes from up to down or down to up. If it doesn't change in concavity, an inflection point's not happening right there. So possible. We also know that we can plug them back into the original function to get the y value and make them into an ordered pair, because part of this problem says find inflection points and then discuss the concavity. So we found the inflection points. When we made our test intervals and we checked them, we see that our graph did go from up to down to up, so those were inflection points, and then we can name those regions on the number line. So we go back and do it. So the first one we said concave up from negative infinity to 0 and from 2 to infinity. Concave down from 0 to 2, and that's how you name that. So in this next one we'll look at a couple more problems.